Hello everyone, I am Chin-Chang Chu from National Kaohsiung University of Science and Technology. My areas of expertise are biomedical signal processing, artificial intelligence, and microcontroller applications. Today, I am going to introduce the NLID algorithm. Today, I will introduce my presentation in 3 parts. First, I will briefly describe the origin of NLID. Second, I will explain the NLID algorithm in detail. Third, I will discuss how probability functions can be used to interpret the behavioral responses of NLID. With that, let's move on to the first part. From left to right, the values of R are 0.25, 0.7, 1, and -0.9. When two waveforms behave similarly in the time domain, the correlation coefficient becomes higher. For instance, when two signals are perfectly matched, the correlation can reach 1. On the other hand, when their responses are less consistent, the correlation tends to be closer to 0. But we should be careful here. A correlation close to 0 does not necessarily mean that the two signals are completely unrelated. It only means that there is no significant linear relationship in the time domain. The signals may still be related in the frequency domain or through nonlinear interactions. A well-known example of frequency domain analysis is coherence, which is widely used in EEG studies, including the assessment of Alzheimer's disease. However, nonlinear correlation analysis is less commonly discussed, even though it can describe complex signal interactions more completely. That is the reason why the NLID algorithm was proposed. This flowchart shows the calculation procedure of the NLID algorithm. First, the original one-dimensional signals are reconstructed into multi-dimensional vectors using phase space reconstruction. Next, recurrence plots are constructed to identify whether similar states reappear over time. Then, the instantaneous NLID coefficients are calculated to measure how much the recurrence behavior of one signal is accompanied by the other signal. Finally, these coefficients are averaged over time to obtain the NLID factor, which represents the nonlinear interdependence between the two signals. Here, I used two simple one-dimensional signals as an example to explain the NLID algorithm. The two signals are x equals 1, 2, 1, 2, 1 and y equals 1, 2, 2, 1, 2. I choose these simple sequences because they make the whole NLID process easier to understand. From the plots, we can see that x shows a repeating pattern, while y changes in a similar but slightly different way. This gives us a good example for analyzing nonlinear relationships between signals. In this case, the parameters are set to m equals to n tau equals 1, which means a two-dimensional embedding with a delay of 1 point. Next, I will use these settings to reconstruct the signals in phase space. This slide shows step 1 of the NLID algorithm, which is phase space reconstruction. We start from two one-dimensional signals, x equals 1, 2, 1, 2, 1 and y equals 1, 2, 2, 1, 2. Here, the parameters are set to m equals to n tau equals 1, so each point is reconstructed into a two-dimensional vector. For x, the reconstructed vectors are x1 equals 1 to x2 equals to 1, x3 equals 1 to x4 equals to 1. For y, the reconstructed vectors are y1 equals 1 to y2 equals to 2, y3 equals to 1, y4 equals 1, 2, as shown in the plots. The reconstructed points reveal the state transition patterns of the signals in phase space. This step is important because it converts the original one-dimensional signals into a form that can better represent their dynamics. After that, we can use these reconstructed vectors to build the recurrence plot for an NLID analysis. This slide shows step 2, which is the calculation of the recurrence threshold. Here, The threshold dth is set to 10% of the maximum distance in the phase trajectory. For x, the farthest two points are 1, 2 and 2, 1, so the maximum distance is 1.414. That means the threshold for x is 0.1 times 1.414, which is about 0.141. For y, the maximum distance is again 1.414. Therefore, the threshold for y is also about 0.141. These thresholds will be used in the recurrence plot to decide whether two phase space points are close enough to be considered recurrent. In step 3, we construct the recurrence plot. After reconstructing the original signals into phase space vectors, we compare every pair of points. More specifically, we calculate the Euclidean distance between the th point and the jdh point, and arrange all these distances into a matrix. Then, we compare each distance with the recurrence threshold. If the distance is small enough, we assign a value of 1, which means the two states are recurrent. If not, we assign a value of 0. By doing this, we can transform the distance information into a recurrence matrix for each signal. This step helps us identify whether similar states reappear in the phase trajectory over time. In the next step, these recurrence matrices will be used to quantify the nonlinear. This page details the calculation process for the construct recurrence plot. In step 4, we calculate the instantaneous NLID coefficient. We start with j equals 1. Next, we multiply the corresponding elements and sum them to obtain the numerator. In this example, the numerator is 1. Then, we calculate the denominator by summing the elements in each column. Both column sums are 2, therefore, the results are gamma yx1 equals 0.5, gamma xy1 equals 0.5. When j equals 2, gamma yx2 equals 0.5, gamma xy2 equals 1. When j equals 3, gamma yx3 equals 0.5, gamma xy3 equals 1. When j equals 4, gamma yx4 equals 0.5, gamma xy4 equals 0.5.
In step 5, we calculate the final NLID factor. From the previous step, we already have the instantaneous NLID coefficients for each j. For gamma, y divides x, all values are 0.5. For gamma, x divides y, the values are 0.5, 1, 1, and 0.5. To obtain the final NLID factor, we simply take the average over all time points. As a result, gamma, y divides x, equals 0.5, and gamma, x divides y, equals 0.75. This means that there is a directional difference in the nonlinear interdependence between the two signals. Specifically, x shows a stronger dependence on y. That is to say, chaotic systems are different from truly random systems. Random systems inherently have no clear underlying rules, whereas chaotic systems are governed by well-defined mathematical equations. However, because the nonlinearity in a chaotic system is strong, even a tiny difference in the initial condition can lead to drastically different outcomes after multiple iterations. This is why weather can often only be predicted reliably in the short term, while long-term forecasts remain very difficult. The Henin map is a classic example of a chaotic model. Although it only involves two simple equations, it can generate rich and complex dynamic behaviors. Here, xn and yn represent the state of the system at the nth iteration, and the parameters a and b control the system's nonlinearity and how it evolves over time. In other words, changing the parameters alters the system's behavior, which can range from stable and periodic dynamics to full chaotic motion. When we set a equals 1.4 and b equals 0.3, the Henin map enters a typical chaotic state. At this point, if we observe its time series, the oscillations appear irregular and almost random. However, these variations are still generated step by step by the deterministic mathematical rules. In other words, while the system appears disordered on the surface, it is underpinned by a definite structure. This example is important because it demonstrates that even a very simple mathematical model, as long as it includes nonlinear mechanisms, can produce highly complex behavior. Therefore, when we study real-world signals, such as brainwaves, ECG signals, or other physiological signals, we cannot rely solely on linear perspectives. Many complex systems may appear chaotic on the surface, but they often hide underlying nonlinear interactions. By using a model like the Henin map, we can better understand how changes in nonlinear parameters influence the system's dynamic behavior. It also highlights why, when analyzing complex signals, we need methods like NLID that can capture nonlinear interdependencies, rather than relying solely on traditional linear correlation analysis. The figure in the lower left corner shows the scatter plot of x and y. From the plot, we can see that the correlation coefficient is approximately -0.37, indicating a moderate negative linear relationship between x and y over time. In other words, when x increases, y tends to decrease. More importantly, the points in the scatter plot do not lie along a straight line, nor do they form a simple linear pattern. They form a curved, dispersed, and structured shape. This indicates that in addition to the linear correlation, the system also exhibits more complex nonlinear dynamic relationships. Even though the scatter plot shows relatively low linear correlation, the two variables in the Henin map still exhibit significant nonlinear dependence. In other words, the interaction between x and y is coupled through nonlinear mechanisms, and NLID is able to quantify and capture this nonlinear interdependence beyond the limitations of traditional linear correlation analysis. This clearly demonstrates that in complex systems, relying solely on linear indicators may underestimate the intrinsic dynamic coupling. Nonlinear correlation analysis is therefore crucial for understanding the internal structure of the system and the interactions between signals. Thank you all for listening. I've attached a handout and the NLID code for reference. If you're interested, feel free to email me so we can discuss further.